Okay, we're going to start our new unit. So the first topic of the new unit is antiderivatives. So in this unit, we're going to learn what antiderivatives are, what integrals are, look at some applications. It's basically a quick summary of everything we learned with derivatives in reverse. So just like the name sounds, an antiderivative would be doing a derivative backwards. So to start with, often the equations, if they use notation, they will give you the derivative answer and ask what is the original equation. So in this case, if our derivative is 4x cubed, working backwards, we're trying to say what would the original have been to get a derivative of 4x cubed. So in the next few days, we'll learn about why we do this and how it's used, but for today, we're just going to figure out what are the steps or how to do the reverse power rule. So we'll start with power rule, just like we started with power rule with regular derivatives. So remember, if I gave you something like y equals 6x cubed, our derivative was we multiplied the 3 down, so we multiply it to get 18, and then we drop the power by 1. So to do the reverse, we have to do it in the reverse order as well. So we actually have to add 1 first. So from the x squared, we'd add 1 to make it x cubed, and then we would divide by 3. 18 divided by 3 would give us the 6. So that's the reverse power rule. And this process is called finding the antiderivative or doing the integral or integration. And like I said, we'll get into integrals and that notation a little bit more in the next couple lessons. But for today, we're just going to learn how to do the antiderivatives. So the formula that's on your sheet, it is written in integral notation, but if you just look at this part, if that was our original derivative, then if we did the antiderivative of that, it would give us the formula. So you can see it's just like our power rule formula, except we add 1 to the power, so it becomes n plus 1, and then we divide by whatever that new n plus 1 power is. A key thing is n cannot equal negative 1, right? Because if I gave you that as your starting equation, and we raise the power, it would go to a 0, and then we'd have to divide by 0. And we can't divide by 0. So this power rule works for every exponent except for negative 1. Okay, so let's try a couple examples. So this first one says, find the antiderivative of x squared. So our antiderivative, we'd raise the power and divide by 3. So we can write it like that, or we could write it as 1/3 x cubed. Both are acceptable. Okay, for the second example, change it to a negative power to start with. So we'd have x to the negative 4. So now our derivative would be raise the power to negative 3 and divide by negative 3. And again, we could write that as a fraction if we want, negative 1/3 x to the negative 3, or we could even write it as 1/3x to the positive 3. So all three of those would be acceptable. Okay, the last one, same thing, change it to a fraction, so it'd be x to the 1/3, so now our derivative would be raise the power to 4/3 and divide by 4/3. Usually with fractions, it's better to write them as the reciprocal, so dividing by 4/3 is the same thing as timesing by 3/4, and that would probably be the best answer, 3/4 x to the 4/3. So now when we deal with antiderivatives, we got to be careful about similar equations. So before we look at the antiderivatives, let's look at the forward derivatives. So for this one, if y equals x squared, we do the derivative of that, we get 2x. For this middle one, do the derivative, we also get 2x, because the 3 would become a 0. Do the last one, it's also 2x. So going forward, the derivatives become smaller. So now when we go in reverse, we don't know which of the 3 it is. So the antiderivative of 2x is x squared plus something, right? It could be a 0 like the first one. It could be a plus 3. It could be a negative 2. It could be any number. We actually have an infinite number of solutions. So what we're going to do is we're going to write this as x squared plus c. And the c is going to represent any constant. As long as it's a constant, can't have an x in it, otherwise that would change our antiderivative. But as long as it's a whole number or fraction or a decimal constant, then we just put a c in to show that it could be any of those options. So here's a different one. So this one, our antiderivative, or our derivative is x squared. So you can see our antiderivative would be 1/3 x cubed. So these graphs are showing all the different possibilities. So the actual 1/3 x cubed is the middle one. Then you can see the one above it has been up 1, then up 2, up 3, or moving down 1, 2, or 3. So that means all 7 of these graphs are all of the same format. They're all 1/3 x cubed, but that plus c just shifts that graph up or down. We do not deal with left or right shifts because that would be a different x location, which would change the slope. But for these questions, doesn't matter where we are. If we picked where these arrows are pointing, you can see all of those locations, the slopes are exactly the same. So that means they have the same derivative, even though the original equation is different. So again, you can see then for this case, our antiderivative would be 1/3 x cubed plus c. So all that means is when you're doing derivatives, just be careful and make sure you put a plus c on every time. And that's basically it. So the notation, again, I could give it to you just in words. So let's do that for the first one. I could just say find the antiderivative of x squared plus x minus 5. So raise our power, divide by 3. The second one, raise the power, divide by 2. The last one, remember that's like x to the 0 if you want to think of it that way. So when we raise the power, we would go to the 1, divide by 1, which doesn't do anything. So this one probably be simpler to write it as 1/3 x cubed, 1/2 x squared, minus 5x. Okay, let's do for the second one. Let's suppose I write it in prime notation. So if I say y prime equals that, now we can do the antiderivative to get y. So we'd raise our power to -1, divide by -1 for the second one, raise it to a 2, divide by 2, and then we can simplify it again. Oh, I forgot on the first one, we should have had plus c on there. And the same thing for this one. Let's put plus c as well. So let's simplify this one a little bit. Let's write it as -x to the -1 plus 3x squared plus c. Or we could even write it as 1/x if we want to do back to a positive exponent instead. So either of those two would be good. Okay, so you can see power rule, pretty straightforward, nothing too complicated when you're working with power rule. The ones that we have to be careful of is working with trig. So for this example, let's change our starting equation to dy dx as our derivative. So again, we want to find just y equals. So with trig, we basically, for today, we're just going to deal with easy trig ones. So if I gave you something like, remember, sine x, the derivative was cosine. So obviously the antiderivative of cosine would be back to sine. And when we had cos x to start with, our derivative was negative sine. So it would work the same if we go backwards. Antiderivative of sine, like the one we have in this question, will be negative cos, because negative sine would turn to cos. So a positive sine would change it to negative cosine. So we get negative cosine x minus 2x plus c. And that's it for that one. The only other trig one you got to be careful of is if I gave you something like secant squared, even though we have a squared and it looks like it's chain rule, remember the derivative of tan is secant squared, so we can just go back to the original like that. We don't need to worry about chain rule. Or the other one that sometimes causes issues, how about if I gave you something like cosine of 3x? So integral, or the antiderivative of cosine, is sine. Keep your brackets the same, but normally when we do derivatives we would times it by 3, so in this case we'd have to divide it by 3. So 1/3 sine 3x would be the best way to write that one. So the last thing we'll look at is there a way to actually figure out what the c number is? So if we're given another coordinate, that means we now have an x and y value, so we should be able to plug that in to determine what those final equations will actually be. So if you get a coordinate or other information, we can substitute and solve for that condition. This process is also called solving differential equations. So we have a derivative equation, we have a coordinate, So our goal is, could we figure out the exact original equation? So it's not solving an equation as if you'll get x equals 5 or something like that. It just means we'll get the entire original equation without the c value. So we just do our antiderivative like you normally would. So take the 2x plus 4, do the antiderivative, would give us x squared plus 4x plus c. Now we plug that coordinate in to actually solve for c. So we get 6 equals 1 squared plus 4 times 1 plus c. So that'll give us 5 plus c, so that means c equals 1. So now we can take our antiderivative equation and actually write in our c of 1. So that would be the exact original equation that passes through 1/6 and would give you a derivative of 2x plus 4. And that's it. So pretty straightforward. You're just basically plugging in the coordinate to figure out the c value. Okay, here's another one written in a different way, but you can see it's still pretty much the same. So the only thing to do in this case is rearrange it first. So bring the minus 2x and 3 to the other side. Now when we do our antiderivative, we'd have raise the power, divide by 2, so we'd get minus x squared. And this would be minus 3x plus c. Now we're going to plug a 5 in for y, plug a 2 in for the x, and solve it. So we get negative 4 minus 6 plus c. That'll give us negative 10, bring it to the other side, would be 15. So in this case, our final original equation then would be negative x squared minus 3x plus 15. And that's our final answer for that differential equation. And that's it. That's where we'll stop for today. And we'll move on to integrals in the next lesson.